today we are going to talk about ESD protection, and it's because it's very important. You can very easily damage chips or devices just by touching some pins or signals which are going out of your board. And it's very important to know how to select these ESD devices, where to place them, or maybe even how to simulate these devices. So that's what we are going to talk about with Andreas. And yeah, let's do it. Let's talk about the ESD. So what is important about ESD? What is it actually?
Yes, hi, Robert. So yes, ESD protection devices are very important when, as you said, protecting very sensitive PHYs or circuits. And so we can, or we should differentiate a little bit between device level ESD and the system level ESD. So here for device level, we usually have or it's valid for chips, ICs, PHYs, for transceivers, and the levels for device level are a little lower because this is due to the fact that you need this device level for let's say production purposes, assembly during all the stages in your production line. So you need to be sure that all the transceivers, ICs you're using are not going to be damaged during this process.
I've seen you have a slide on this, so just to give people idea what kind of difference is between this chip level ESD protection and what we can actually do on the board. So I think you have table where you yes, exactly, this is the table.
Exactly. This is an example. So we have different PHYs or transceivers here, and for different applications also. And you see the on-chip robustness, those values are taken directly from the data sheets. So you can achieve higher, so 8 kV, so higher ESD robustness for some of the CAN transceivers here, for example. This is usually because CAN transceivers are compared to others, some high-speed PHYs are not very complex. So you have a lot of chip area inside the ICs, which you can really spend for on-chip ESD protection.
Okay, so basically, if you would like to integrate ESD protection on the chip, you will need a lot of space on the chip. That's why maybe complicated chips, they are not so robust. And
yes, it's.
And I would like to ask, is 8 kilovolts a lot or is not a lot? What does it mean? Does it mean like you will not normally damage this device by using or touching this when you are at home or something?
Yes, so 8 kilovolts is already very good, let's say. There in let's say in the most for most applications it will be enough. And if you look on the requirements for some or from some car OEMs, for example, so at least for European car OEMs, this is okay. So there are some car OEMs in other parts of the world which wants to have more. So they will want to really have a more safety there and safety margin. So they require more, so up to 15 kV or more. But
2 kilovolts is not enough.
2 kilovolts is for handling during assembly and process. It's usually enough. So this is really one of the, let's say, major requirement for ICs. 2 kilovolts typically the minimum.
Okay, so that's basically to protect when someone just take the board into hand, and that's
yes.
And
just to take to when he touches the IC for example, or when the IC is in the process line is kind of has a significant risk to touch any other area or component which might be charged. And this 2 kV is usually a good value to be robust during all these processes. Yeah.
Do you have some kind of standards listed somewhere? Or?
Yes, there are some ISO standards. Maybe you can go on the slide back again.
Okay.
Yeah. So here there are some standards which are important. So here for device level, there are typically these JEDEC norms are very important. So there are several models derived in the last years, which are tested then on device level.
Can we talk about this a little bit? Because I've seen this human body model a lot in datasheets, but I have no idea what this means.
Human body model usually represents the discharge from a human human body, sorry, and this is usually representing then with an equivalent circuit. And this equivalent circuit is then including a capacitor, which is roughly 150 picofarads, yeah, and resistance. So the resistance to discharge the capacitor, and the resistance value is roughly 1.5 kilo ohm. Yeah.
And what is the voltage?
The voltage is here different, as again 2 kV is usually the minimum what is required for ICs, but you can test up to 15 or 30. Yeah. But yeah.
So I understand now. So basically, human body model, machine model, charge device model, these are basically the kind of circuits which are representing different situations or different
scenarios. Yeah.
Okay.
Exactly.
Okay. And a system level, so system level would be the components which we place, for example, somewhere on our board away from the chips. And I see there are some other standards. So can we talk about this a little bit?
Yes, so system level is exactly what you said. We on system, when your ECU, your module, whatever you can call you want, however you want to call it, is really in the field in usage, and there are different risks they can appear. Yeah, so it means also again human body can be. You can be loaded up to several kilovolts and can touch your system everywhere. Yeah, so on the display, on the cover, on the
pins, connectors,
on the pins, and everywhere.
buttons,
yeah. Also, different components like cables can be charged up to several kilovolts. Yeah, and there is also some pulses coming from power over data line, applications. So they also is a risk when you connect and disconnect inductive loads. Yeah, there might be very significant pulses coming in. So all these system risks are covered by this system level testing. Yeah, and the most standard used here is this IC 61000-4-2. Which is describing a typical ESD pulse, 100 nanoseconds long, and the equivalent circuit for this is 150 or 330 picofarad over a 330 ohm resistor. So you see, compared to a human body model, you have much more energy inside, which you discharge then. Yeah.
Okay, I think you have some slides about this test. So it's the next one, I think, isn't it?
Yes, I can show you some more testing on one of the next slides.
So basically, when someone design a board, what they can do, they can rent ESD gun. If they don't want to buy, they can rent it, and they can test robustness of their boards or systems by themselves, just to be sure it will pass before they send it and pay for certification or something. Yeah. So how do we do this test? What do we need to do?
So there are several tests can be done here on system level. This is an direct discharge, indirect discharge, and air discharge. So those three are typical for automotive, let's say. Yeah, and
can we show the gun first so everyone see how it looks? Or can we find it somewhere on internet? Just maybe search in Google for ESD gun or something.
Yes.
because I would like to say there are different kind of devices, and on them you can actually set different voltages, number of pulses, and then when you are using them for testing, then you also use this air discharge or direct discharge. We will talk we will talk about this. What is the difference? But I would like everyone to know how this looks.
You cannot see it, right? Because I'm still sharing the. Can I?
You can just
let me share the screen. Can you see it now?
Yes, I can see now. Yeah, okay.
So this is how a typical gun can look like. So several versions, let's say, but so this kind of usually the modern ones, they have a display, so the generator here, a display where you can select the pulse voltage, and also how many pulses you want to apply, plus, minus, and so on and so forth. And you have a point here, to a pointer. And this pointer is also can be different, depends on if you want to have a contact discharge or air discharge. So for air discharge, it's usually more rounded. For contact discharge, you have more really sharp one.
And what else we need? I see there is this table, and then I think we need the metal plate or something where
yes. If you really want to make let's say compliance testing, then you need a standardized, let's say, equipment or environmental. So this is including some grounding resistors here, very important, copper plate or a metal, some kind of metal plate, and you also need to take care about the air conditioning. So humidity is very important, because especially for air discharge, the discharge itself is really dependent on the ions in the air. So when you know more, the humidity will for sure impact this. This one.
So maybe now we could explain what is the difference between this air discharge and the other. So we can go back to your presentation.
Let me go back.
And also, I would like to point out, you already mentioned this. When this test is done, you need to test it for both negative and positive voltages.
Yes, you do usually positive and negative. So typical 10 plus and 10 minus. This is the typical testing procedure. You're right. And yes, this direct discharge is this where you use this ESD gun and with a very sharp pointer, and you put it on any of the pins. This is
everywhere where people can touch.
Exactly. Yeah, exactly. For us, very important, the IVN interfaces, so the connectors where all these I/O pins are going in and out. And and you do it, which up to a certain kV level, let's say 8, 6, or 15 kV, whatever your customer is requiring. And after this test, so you do it plus 10 times with a positive, 10 times with a negative pulse, usually. And then after this, your device should be working without any restrictions. So the same as it was working before.
I think there are different levels. If I remember right, there is something like nothing happened and everything is working perfectly fine, or device can reset or freeze, or it can be damaged. I think there are these kind of like different levels.
Exactly. And for this special test, this is done in unpowered mode. So you have your model. This is not powering, not running. You put it on this metal plate on your ground table, and you shoot the pins 10 plus, 10 minus, and then you power it again and then see if is everything still working correctly. So
what is indirect discharge?
Indirect discharge is kind of a little more specific for automotive, let's say. And here the device, so your ECU, your PCB, is in powered mode. In powered mode, and it's usually placed when you have for example, a transceiver and a receiver combination. Your system, you have in between you have a harness, roughly 2 meters long. This for all car IMs roughly 2 meters, and you power your system on. So you have really data transmission from TX to RX, and you see if you have a display here, for example, you see some pictures, very nice, everything is clear. And then what you do is you put your harness here on some ground islands. Yeah, those ground islands are connected to ground here on this point. Here. Yeah, and you shoot with your ESD gun on those islands. So on all these 3 positions. Yeah. And the requirement here that your device should have stable communication. And then there is some steps in this requirement, as you said. So if your device during testing will go and will reset or will freeze or something is happening.
Usually on display you can see some disturbance or something.
Yes,
yeah,
exactly. Then it's some kind of detailed requirement from your customer. Is this allowed or not allowed, or should it be everything's fine when you reboot it again, and so on and so forth. So there are some steps you can differentiate and discuss between your company and the customer.
And air discharge.
An air discharge, yeah, this is very difficult, let's say, and we usually do not do a lot of air discharge because it really depends on everything, on your environment, on the air conditioning, on what is the angle of your ESD gun, how to put it, and air discharges usually apply to every touchable, reachable surfaces, displays, buttons, connectors everywhere. Yeah.
And basically, I think if I remember right, it works like your ESD gun is charged, and you go closer until there is the spark,
Yes.
and that's basically the air discharge. So you don't touch directly, but you wait for the sparks.
Yeah, you wait for the spark, and you do it on any surface you can reach. Yeah, if you have a display and buttons in your interior of the car, for example, you need to test it on each of these buttons, on each of the point, or several points on the display, and so on and so forth. So really, as you
direct
said,
discharge is not done on everything.
Usually on the connector pins.
Okay.
Yeah. On the connector pins, and maybe some car OEMs during car testing. Doing this on, let's say, from behind on some screws or so. Yeah. So whenever the service man who is putting this system later on during car manufacturing together, whenever it can be reached from the serviceman. Yeah. So it also can be done, but it's usually, so most important probably is really on the connector.
Okay. So basically, we know that to protect our chips from these ESD discharges, we may want to use some external components.
Yes.
So let's find something. I think you have a slide about this kind of components. Let's jump to this slide. I'm very curious. How do you decide on what kind of component you would like to use for USB or something? I think you have very nice
even this one.
Yes, exactly.
So yes, it depends really on the application, what you have on interface you want to protect. This is really, so I mean, 30 years ago or 40 years ago, there probably was only a few interfaces, and they did not require much. Yeah, and you could use pretty much any ESD protection, put it there, and it worked. Yeah. But now, so we have a lot interfaces, and they are kind of very different. Yeah, the main difference is the data rate or the speed creator. Yeah, so there are also different requirements based on applications, and here you need really to look which application you have. And usually, so the way how we sort it or cluster it, we do it per application. So for example, for LIN, when you go on our web page, you can select automotive ESD protection, and then it's for LIN. Yeah, you can click on LIN and you will get some already a good selection.
I don't even know what LIN means.
LIN is an interface. It's a one-line interface. It's working with a 12-volt battery. It's very low speed, yeah, 20 kilobits per second. But it's very cheap, yeah, and you cannot put a lot of data through it, but it's easy to use. It's very cheap, and it's still in usage in climate control units, or let's say very small or very low data rate applications. Let's put it this way, yeah.
So okay, I have a question. So when looking on this table, basically, when selecting ESD protection for specific interface, I see biggest difference is, for example, capacitance. Higher speed of the interface is, you would like to use probably lower capacitance.
Yes, much lower capacitance. Yeah, we have here some overview. Rough overview, not really exact, but the rough overview on the capacitance for different interfaces, and so there's capacitance for the ESD protection device over the data rate, and here we put some of the interfaces. This is more for automotive, but it's the same. The method is so the same for mobile and consumer. So as we said, LIN is very low, 20 kilobit per second. You can use there up to 100 picofarad for the ESD protection device. Yeah. So because capacitance load is not very important there. Yeah, and signal integrity is not very important there. But when you go, let's say, to CAN, so you there have up to 2 or 5 megabit per second, especially for CAN FD. There's CAN XL and FlexRay going up to 10 or even 20 megabit per second. So here you really need to think about already that not too much capacitance is on your bus. Yeah, because you have not only one node for CAN, you have usually several nodes, and all these nodes are on a bus, and you will add with each of the nodes a capacitance load, let's say, to your bus.
What about voltage?
Voltage is very important.
So how much higher, for example, the protection voltage needs to be comparing to the interface voltage, or how do you choose it based on the voltage?
This is a big topic, let's say, or can be a big topic. So maybe you can put in some examples. Yeah.
Okay.
Here's a, let's say, very basic example is CAN controlled area network. Here the requirements are on the voltage, so this standoff voltage typically. The standard voltage defines a value. Up to this voltage is the ESD protection is very, very high ohm, so not reacting on any, so not turning on. Yeah. So also very low leakage below 1 nano amp. So pretty much invisible. Yeah. And so here, for different board nets, you need to look at different standard voltages. For 12 volt, it's typically 24 volt. Yeah, 12 volt board net, it's 24 volts for the ESD protection device, and this is defined here in the ISO norm, but not directly for the ESD protection device. This is kind of tricky. So there is, let's say, for all these LIN CAN applications, which are on the market since 20, 30, 40 years, there's no really dedicated definition how the ESD protection should look like. So only indirect. Yeah, you can take the values indirectly, and this ISO norm is one of these norms, and there is stated that the system in a 12-volt board net should be robust and not clamping below 24 volts. So
what about USB? Here it is clear, for example, if you are using this specific CAN for 12 volt, then protection should start working at 24 and higher.
Yeah.
But for example, if you work with lower voltage interfaces,
Yes.
which are using signals like 3 volts or 5 volts, then how much space you need to protect it, or when this protection should actually start working?
Yes, so usually when so for sure above the swing voltage, yeah, and you need to look then on the maximum voltage which can be on your I/O data lines, yeah. This is different, and I think for USB, the ESD protection devices, what we have is are from 3.3 volts to 5 volts roughly. Yeah, so this is the region. So much lower voltage range. So not 24. Yeah, this is much too high. So you need for high-speed interfaces usually, and for USB, go to down to roughly 3 to 5 volts. Yeah, in some applications even more, even below 3.3 volts, because the voltage swing during data transmission is below 1 volt. Yeah. So it's not critical, but then you might have some different other modi on, and which allow to go up to 3.3 volts on your own lines, right? And you need to be prepared for this. So it's not allowed to. It would be not good to turn on the ESD protection devices during this. Yeah.
So, but I think when very often when I'm selecting ESD protection for specific interface, very often manufacturer will actually say like this protection can be used with these interfaces or this one.
Yes.
So that's something what should help people to decide how to basically choose or select ESD protection component for specific interface. Manufacturer will help them. I think that's what we've seen on this table on the page 11, because you had these specific chips recommended for specific interfaces. Exactly.
Yes, usually there's in the datasheet there's a hint. Okay, you can use this device for this or this application, or on, as I said, on some of the web pages of vendors, and for example on ours, you can really go to ESD protection for Ethernet and then choose some device which is package voltage range and etc. Yeah.
So what is, can we talk a little bit about this voltage break, voltage halt, or voltage trigger, so we understand what is this about?
Yeah, this is might be very important, yeah, to differentiate a little bit what is the selection criteria, let's say, how to choose the ESD device when you want to look a little deeper into all these values. And I also want to point out here that, or make it on two examples. And the one is the Zener, so the classical Zener ESD protection. This is the petrol colored one. This is probably the one which the most of the people or design engineer, hardware engineer know from school, from the university. This is the classical one. So it's usually this is shown for bidirectional. So in both directions, it's the same. So the device is not turning on. Yeah, so it's very high ohmic up to a certain value. This is this the standard voltage. Yeah, reverse maximum voltage. This is the VRWM, and here in this range, and the leakage is very low, so below 1 nano. And once you achieve this, the transition area starting, let's say, between the standard voltage and the breakdown voltage, VBR. So this is where the device is, let's say, starting to turn on slowly, so the leakage will increase. And once you reach the breakdown voltage, for Zener, classical Zener protections, this is when it's when it's starting to conduct the current. It's really when it breaks down. And then it goes, let's say, up with a certain dynamic resistance.
So basically, on the component, we will still have same voltage, the VBR breakdown voltage, even if the current is higher and higher and higher. It will still be the same or very similar voltage. But there is also this second line, which I guess is better because the voltage will actually drop down if I understand right.
Yeah.
It will drop down, even the current is rising. So
yes.
basically, that's good because when the voltage drops down, it means it's protecting the chip better. It's not
Yes.
the chip is not really receiving the very high voltage.
Exactly. So this is the big advantage of the snapback devices. Yeah. So as you said, so you once you achieve the trigger voltage. So for snapback ESD protections, it's not breakdown voltage. It's usually called trigger voltage. So once you reach this, it's snapping back to a lower value, and this is called here. The point called here is holding voltage VH, and then it goes here up with a certain dynamic resistance, typically below 1 ohm. So the dynamic resistance is below 1 ohm. So this slope is here very high usually, yeah, but it depends for sure. We can have an example later on. I have one example which is showing different dynamic resistances which are having impact on, for sure on the clamping. But as you said, this is exactly the point. Yeah, when having the snapback devices and so these C pulses coming and the device is triggering and clamping at a certain clamping voltage, VCL. So here, yeah. So the clamping voltage is between the snapback device here and the classical Zener for given breakdown and trigger voltage. So when breakdown voltage and trigger voltage of Zener and snapback device are kind of in the same range, yeah, the clamping voltages are very, very different. And this is a big advantage because the clamping voltage, this is what the PHY sees during ESD protection.
No, I think
better, yeah.
I think there are two big advantages because basically you have this higher voltage on the chip only for very short time.
Yes.
Is one advantage, and the second advantage, I guess, because the voltage is lower, it means also the power dissipation will be lower on the device.
Yes, sure. And even if this overshoot, let's say, as you said, so the PHY will see for sure, and so the ESD protection will need some time to turn on. It's usually a few nanoseconds only, so it's very fast. And in addition, if you have a ESD protection device close to the connector, so I mean far away from your PHY, so you will have there some in trace length, so a few centimeters maybe, and every centimeter, every millimeter of the trace length has a certain inductance, a few nanohenry, yeah. And this inductance, so this is not a classical inductor there, so it's a distributed inductance, but still it helps when it comes to overshoots, which are very short duration of time, a few nanoseconds. So those short overshoots, let's say, can be at least a little damped by the natural inductance of the trace. And when you have a ferrite or you have a common mode choke there for differential signals, common mode chokes in typical ranges for CAN or automotive Ethernet is roughly 100 microhenry. This is a lot of inductance, which is in between your PHY and the ESD protection. So usually those overshoots which are coming over the trigger voltage of the ESD protection will be swallowed down by this inductance, and then this is a very good combination. Yeah.
Okay, so you already started next topic, placement.
Yeah.
Where we would like to place ESD protection devices?
Yeah, so we have so in general, we always recommend to do it really close to connector. Yeah. So because as we said here, even if you do not have a common mode choke, you have traces, and those traces have distributed inductance, and you really should take use of this, of this inductance. Here is one example. So this is not a let's say quantitative example, but just qualitatively want to show how this inductance can impact the current which is flowing into the into your receiver during ESD pulse. When placed here close to the connector, as we said, the peak, especially the peak, will be reduced by the inductance. So you see it here in the
So
plot.
the blue line, that's the blue line.
Blue line, yeah, the blue line, yeah, you can see it clearly. Yeah, that's roughly double the value. And but also the shoulder, it's
lower.
It will be impacted because you for sure you have a voltage drop over the it's a little, yeah, and when you have a real common mode choke, it will be a few volts, let's say, but for the distributed inductance, it's by far not that big, but a little. It will always be a little improvement, even for the shoulder. Yeah.
I think there is one very easy way also why it's practical to place the ESD protection as close as possible to the connector is because once I remember I was testing one board, and when basically what may happen, even if there is no ESD protection, the discharge may happen everywhere on the way to the chip. So it means if your ESD protection is not very close to the connector, the discharge may happen somewhere on the way between the connector and the protection, and it can damage something else on your board. It will basically be in your board because you may have maybe some components very close to the track, or there may be via, I don't, but I've seen sparks between tracks, for example, or something like this.
Yes, it is exactly. Yeah, very, very good example, Robert. And the MC engineers using filters, yeah, when filtering DC-DC converter, for example, yeah, so the best filter design is, or the filter position is, yeah, let's say very close to your DC-DC converter, because you want to filter the noise directly at the source. You know, this is the main idea of filtering, and all EMC engineers know this. And in here is pretty much the same. So the source of your noise, let's say, is the connector, the virtual source, because this is where you apply your pulse, and you want for sure to filter it
as soon as possible.
As soon as possible to go, and then it's far away from the phi. So even if you have the pulse in your ground plane, so you are far away from the phi, so the risk of having troubles due to ground bouncing on or something is or ground currents, it's much more reduced. Yeah.
And also I would like to point out it's recommended to do direct connections. So for example, if you have pins or pads from the connector on top layer, then place the ESD protection on the top layer and make direct connection between the connector and ESD protection, rather than going through via down and placing ESD protection on the down, because again it may even discharge somewhere inside of the via to the planes, or I don't know.
You can.
Is it right? I don't know. I just read this and this is what I imagine.
Yes, you in a really, let's say, risky layouts, you can control your ground current somehow, up to a certain point, and you should use this, you should, if you have really a sensitive phi, and even a very small amount of current, which is kind of in the area of the phi, will impact the phi somehow, or can even damage it. So you can make modify your grounds in the way that the pulse will come back out of your PCB over the connector shield, or over the ground pin, which is placed somewhere close to your signal pin, or so on. Yeah, this is very good recommendation, Robert. Yeah.
Okay. I think on some of these pictures you have also the distribution of the current.
Yes, this is basically the visualization of the same idea. So having these ESD protection close to the connector, we tested this for 3 different scenarios based on automotive Ethernet topology. So it means we have a phi here. We have this is a common mode choke. Here we have some common mode terminations, so resistor capacitance, and here we can place an ESD protection, and here's the connector. And so there's no protection at all in this circuitry. Then we have the same circuitry, but with ESD protection, let's say classical position, which was used 10, 20 years ago, just between the common mode choke and the PHY itself, so close to the PHY, let's say.
Mm-hmm.
And then we have the third scenario here. This is the close to the connector, which is more or less reused by the Open Alliance Standard Committee. And what we did here was, for all these three scenarios, we applied a pulse here on the connector,
Mm-hmm.
and looked on the current distribution during this ESD pulse. And this
How
is what
did you look on this? I'm curious. Is it simulation, or you use special camera? Or I have no idea.
This is the EMI scanner, which is basically
okay.
This is basically an inductive probe, which is tracking the magnetic field. And so you can do it several times just to track all these, to go over the probe, to go with your probe over the whole PCB, and then you can collect all the data and represent
okay.
the current. So from the magnetic field, it's directly directly connected to the currents, and then you can visualize the current, which are surface currents are flowing on the PCB. For sure, only on the top layer, because the lower layer, so the inner layer is not visible very much because of the grounding layer above. So, but this is what you get, And red one means very high density, current density, and blue means so very low. And for these three scenarios where you have no protection at all, so it means that for sure you see here a lot of magnetic field and currents around your common mode choke, because there's a magnetic element, let's say, inductor. But what is very important, you see some portion of the current which is going here into the PHY.
And what is between the inductor and the PHY? There, Here 0 ohm resistors. What is there? I don't know.
Yes, this is only a place 0 ohm resistors, so it's only a
it's a jumper, because
jumper.
Okay.
Yes. So the classical or the ESD protection between the common mode choke and the PHY. Here you see a lot of current here, and so big portion also covered here by the ESD protection, but you still have some current going into the PHY. And here, the one where you have the ESD protection here at the connector, this is even in this visualized experiment, the best one. So you see a lot of current here close to the connector.
So everything is basically discharged in this very small area close to the connector.
You protect everything. You protect the PHY, you protect the common mode choke, you protect the common mode termination. So it's everything protected here. So this is a big plus. So you can be more flexible with the selection of all these periphery elements, so the resistors, common mode chokes, when having this position.
Okay. So can we simulate this?
We can simulate. So we now can simulate on circuit level. So meaning that we can use system efficient ESD design simulation. So this is the method where you can build up dynamic models for ESD protection devices, which can handle very dynamic pulses. So ESD pulses were from 0 volt to 30 kilovolts. It's going up in 1 nanoseconds roughly, so or even less. So very dynamic, very transient pulse, and so you need really specific models, and this seed models can handle this.
Okay.
And you can use them to make some predictions on circuit level even.
So I think
this is working right now.
You mentioned on the slide number 21. I think you mentioned there are actually two kinds of models. one is for
Yes.
signal integrity and one is for
Yeah.
ESD, or
Yes, exactly. So from ESD point of view, so once on your interface, so you cannot resolder the ESD protection. So you cannot put it when the ESD scenario is coming. So and that's why we need to consider both two scenarios. And the one is for sure very important for us is the ESD scenario. So very high voltages up to 30 kilovolts can appear here. And this is the case when the ESD protection is active. Yeah, here the current needs to be clamped down to ground very fast and very efficient. Yeah, here this is one very important scenario. But the other one is the data transmission. This is also very important because in this scenario, the ESD protection is a passive component, and it should be more or less not visible for the signal. And usually you can say, okay, the ESD protection can be represented by a capacitance in this case. Yeah, and the capacitance value is given then in the data sheet. So roughly out of our picofarad range.
So for simulation, these are two different models?
Really different, yeah. And
also they are different simulations, I guess.
Yeah, different simulations. So for data transmission, we do provide or do have scattering parameters. So
S-parameter model.
Yeah, S parameter. So the touchstone file, for example, some people know, you can use those files and those data and the most of the modern solvers, yeah, and tools. So ADS or CST or HFSS or a lot more, yeah. The most of them can handle this IEEE standard, this touchstone.
And how do you simulate this ESD even? I'm curious. So what kind of models you use there?
Yes, here we do make a lot of measurements, transmission line pulse measurements. I do not have a slide for this transmission line pulse, but this is a very, let's say, so similar to ESD pulse. Yeah, it's a rectangular pulse which we apply on the ESD protection, but it's in an impedance controlled area. So we do apply these pulses in a 50 ohm environment. And this is very good because you do not care about the angle of your ESD gun. You do not care about the impedances because the impedance of ESD gun and your transmission line will differ, and then you will get reflections. And then this makes the ESD measurement up to a certain point not really good reproducible. With transmission line pulse, you have a very good defined rectangular shape, yeah, a very good defined pulse. You are in an impedance controlled environment, so you have very low reflections, so you can investigate your ESD protection much better. And this is really what we are using. And we shoot a lot of pulses with increased voltage and increased currents, and we collect all this TLP data and put it in a model, yeah, in a behavioral model. And for and we can do some modifications, some tuning of the model, and can use them in for ESD simulations.
So even also for the first case, you create S parameters model, but it's different one.
For the ESD scenario. Yeah, there are also scattering. You can also create scattering parameters there. Yeah, but the different ones. Yeah,
different. Okay, and then when you are simulating this, you use same software, same everything, just the impulse and the model is different.
Not the same. So usually for this ESD simulations, this is a system efficient ESD design. We use ADS or LT Spice. So mostly ADS. ADS is because other more functions there. This is we use it more for signal integrity simulations. Yeah, for data transmission simulations, we do have. You can use also ADS, very popular, but you can do CST, so Microwave Studio. You can 3D solvers. You can use HFSS, so a lot more. Yeah.
Okay, you can click on page number 23. I'm curious, what is that?
Yes. This is the, let's say, the signal integrity simulations, which you can do with ESD protection devices. And as I said, a lot of methods and tools created from very good high-speed engineers in the last 20, 30 years. And the most of them you can use for for ESD protections. Yeah, you can do simulations in frequency domain. This is the classical scattering parameters. Yeah, an example showing the whole channel. So channel means for one PCB over a long cable, 10 meters, to another PCB with and without ESD protection device, and frequency domain. So
why they are so different? What are the blue lines and the red lines?
The blue lines are the insertion loss, so the transmission S21, yeah, and the red and magenta, this is the reflection, yeah.
Okay.
S11 or S22, yeah.
Okay. So what else you have in this? I think I asked everything. I'm curious what else you have in this slide. So go on the top.
Maybe also time domain.
Okay.
One word to the time domain. So time domain is also possible. We do a lot of TDR. We have eye diagram simulations. We can do also, or we can have also eye diagram measurements for sure. But you can do put everything. So just a simple random timestamp you can throw on the ESD protection, so on the ESD protection device, and show what is the impact. Yeah, and this is just by having the very good measured scattering parameters. Both domains are connected with a Fourier transformation. So, and as I said, most solvers can handle the Fourier transformation, so really no problem. Jump from time domain to frequency domain. Here a lot of big portfolio measurement and simulation portfolio, sorry, is available here, yeah, and we can support.
I just remembered you have one slide to compare different packages or influence of using ESD protection component in different packages. Oh, okay, this is the one.
Yes, this one just showing an example. This is, yeah, how this is in frequency and also time domain. As I said, you can use the scattering parameters in frequency domain and make a eye diagram simulation, so in time domain. And this is done here for two different devices. The very special thing is that both devices have roughly the same device capacitance, 0.45 here and 0.4 here, the lower one. But there's very different eye diagram, yeah, and also you see here kind of different scattering parameters, at least for higher frequencies.
I guess it's because of inductance.
Because of package parasitics, yeah. This is the main reason, yeah. And inductance is here one of the main driver, let's say, because here in this package, this is a, let's say, much more compact package of 0.6 times 0.3, and here you have 1 times 0.6, so it's a little bigger. But we have here wire bonding, so we have really wire bonds from one die to another. And here, no wire bonding is used. So
from the pad to die, that's what I mean. Or
yes, in some designs there are 2 dies. So if it's a bidirectional device, you need 2.
Okay.
So on one.
Oh, between the 2 diodes inside of the.
Yes.
Okay.
Yes, but you're right. If you have a unidirectional device and you only have one die on one pad, so you need to connect to the other pad. Yeah. You're right.
Okay, so if there is wire inside, then this is very nice example that even to see how big difference can be actually between different components. They may look like same, but performance is very different.
Yes, and it doesn't mean that one device is better than the other. It's always when you ask the EMC engineers, the most used answer is it depends, yeah. And here it depends, yeah. It depends on which frequency, for example, frequency range you're interested in, yeah. If you're interested in frequency range below 1 gigahertz here, yeah, then also this device this package is very good, yeah. Up to a certain a few gigahertz, or 2 or 3, it's not too bad. But if you really go to,
sorry for interrupting. Then question would be like, then why you should not be manufacturing and selling only the better devices? Because I guess there are also different parameters.
Parameters, different costs and different requirements, right? So here this package is mostly used for mobile and consumer applications. So it's very compact, but the main reason is there is no sidewardable flanks. Yeah, because there is no automatic inspection, automatic inspection used in mobile and consumer. For automotive, you need AOE, so automatic optical inspection, just to be sure that your solder joints are very well defined and you solder very well. And here is a little, maybe also not the best example, but a little, let's say, sidewardable flanks is seen here. And this is for some other packages, there are this sidewardable flanks really well defined here on the sides. Yeah, so the solder can really go on these flanks, and you can inspect the soldering very well.
I had no idea that's why it is there. I thought it's there because just it's a little bit bigger or something. So it is intentionally there.
This is intentionally there, yeah. And there are even some other examples. Maybe we can go on our. Can you see the screen still?
Not yet. You can share it. Yeah, share it. I don't see it.
Give me a second. I will just Capacitance 6 PD. I will first find the package. So let me share again the screen.
Okay.
So this is what is yeah, this is our page. So yeah, this is an example of sidewardable flanks. You see here this piece which is going into the side of the package, and when you solder, your solder will be covering the sides, right? And you will see kind of flank here going to the pad, down to the pad, right? You see, so from here, the solder will be go
a little bit
down
up there,
here, yeah. So, and this is required, yeah, for the most of automotive applications. And for mobile, it's not required, and that's why there are really differences in the package and package technology, and so on and so forth. Yeah.
Okay, we can go back to your presentation.
Yeah.
And just go on the top, and we can go through the slides what we didn't talk about.
Okay.
So I think we went through all these. Number 5, maybe.
Yeah.
Okay, we talked about this one. Number
maybe this one.
Okay, we didn't talk about this one.
Yeah. Well, maybe a little, but not in detail. So once these steeples, so the thing is that you really want to these steeples not to enter your IC, because once it's entered, and it doesn't matter in what was the coupling path. So it's directly discharged or an indirect discharge. Once the pulse is inside your IC, you might be in trouble. Yeah, you might be, because yeah, as we said, especially for high-speed interfaces, you will have very sensitive CMOS technology there, and once damaged, or yeah, you can not use.
So basically, the ESD pulse can damage, for example, the transistors on the pins.
Yeah.
Okay.
And the transistors are when I do not have the slides available, but we did some investigations of the breakdown voltage of on-chip ESD. Yeah. And this is really clear dependence between low data rate CAN transceivers, for example, have kind of higher breakdown voltage.
They are more robust.
They are more robust, yeah, exactly, and very high-speed infotainment ICs, for example, they have very low
Super
breakdown voltage.
sensitive.
And this is
And
because even the clamp in the internal clamp need to protect the very so low, very sensitive devices here, very sensitive transistors, and those transistors are also very. So the gate oxide is very thin, yeah. So and the voltages here are very small, and that's why you need to go to lower voltages from the on the internal, the on chip, yeah. And that's why we're also then reacting on this low voltage with an external ESD, having low voltage external ESD protections for high speed devices. This is kind of all connected, yeah.
I would like to point out, number of people told me that if there is ESD damage, it doesn't necessarily mean the transistor or something inside of the chip will be completely damaged. It may, for example, work somehow, or sometimes it may work for some time and it will then be damaged, but much sooner than it would be expected. So even if there is no visible ESD damage, it still doesn't mean there was no damage.
Yes, this is a very good point. And usually when you want to do a very detailed analysis, you do a functional test, yeah? And which also means you should ESD and power your system on and see if your bits and bytes are traveling very well. So no damage on this, yeah. And this is a very sophisticated test, and you need a lot of diagnostics there, but you can do this, yeah. And this is much more precise test compared to just looking if it's damaged or not damaged, yeah. So it can be kind of not broken, but damaged up to a certain value that you cannot use it in a real life. Yeah. So, and this is, we have several examples with several customers and file manufacturers exactly on this case. So we recommended ESD protection devices, and what they did is they put it on the device, on the PCB, tested so short ESD pulses, and then they did diagnostics, did functional tests to look if there is even a little damage or not. Yeah. Very good point. Yeah.
Okay. What are the next slides we didn't talk about?
I think maybe this one.
Okay.
Just to show, because we have talked about this, let's say, modern snapback devices, and this is an example. Yeah. So we have some, let's say, legacy devices which are 10, 20, 30 years old, and we have an evolution there. So, for example, this is a PSD1 CAN, and then we have the PSD2 CAN. So they will even here we had an improvement. If you remember, low this again current over voltage, so our IV curve. And as we said, so lower voltages, low clamping voltages is better protection of the phi, and this is the evolution. So old, very old ESD protection, then not very old, but old. Some improvements is done here, but then we have new technology here with the snapback, and really having a very straight IV curve here, which is showing that the device is very robust, with very constant and lower clamping voltages. So just to give you an idea how modern ESD protection devices behave and what are the benefits of them. Yeah.
Okay. Next.
Okay, maybe
I think we talked about that one.
Yeah.
Number 13. What is on number 13?
13. This is scattering parameters. We talked about scattering parameters. So basically, so all these discontinuities can impact the scattering parameters, and this is so for ESD protection devices, the most important parameters are the insertion loss and the return loss. And this is two examples from data sheet. So insertion loss is more or less the transmission, so the transfer function roughly, transfer function of the ESD protection device.
So basically, the first graph, again, I would like to maybe explain a little bit. First graph means that up to, I don't know, what is it, 10 or 9 frequency, there is no loss. But when we go below 10, how do you say 10 up to 10, or what is it? That is gigahertz.
This is 10 gigahertz is here.
Yeah, okay.
And here we have almost 20. Yeah.
So, but the loss is like -1 decibel. Okay.
Yeah, so it's a high-speed ESD protection device. So what I've chosen here, so the loss is not very big here. Yeah.
So it means we lose some kind of signal, but still okay. Yes. And the return loss is, so these are the reflections, or what is it?
Yes, this is a reflection. This is a return loss, exactly. Yeah. Just it's more or less very low at low frequencies, but starting to increase here with the frequency. And at 10, 20 gigahertz is between 15 and 20 dB. And 20 dB is in scattering parameters, it's 10%. So it means that here at, what is it, 8, 9 gigahertz roughly, the reflection on the ESD protection device will be roughly 10%.
Okay, so basically the total loss is one plus the other one?
One plus the other one, how, what?
I mean, when we compare the signal on the left in the picture, if there is some return loss and there is insertion loss, it means on the right, the signal will be insertion loss plus return loss?
Not this. So not that easy, because you need to calculate it by. This is related to power, so you need to make a power to 2 and then square root. So it's not that easy in scattering parameters but you need to look on the total power then, and then you will get the total loss, let's say.
Okay, yeah? Maybe it was not very clear question, but I hope people will understand or they will ask. I don't know.
You can. That's a good point. You can get really a good idea using the scattering parameters how much of your signal you will lose or you will transmit. Yeah, this is exactly what the idea behind having scattering parameters is. Yeah, and they are related to your system impedance, and this is very important in high-speed signaling, right? So whether 50 ohm or 100 ohm, so single-ended or differential. Yeah.
Okay, so what is number 15? Oh, I think 15, that's okay.
This is what we had. Maybe what we did not have is those 3.
Oh yeah, this was an interesting one.
Exactly. So this is can be a very big topic or bigger, but we can cover this on 3 slides just to mention the importance of this. Yeah. The thing is that when having the very compact system, so means you have connector and the PHY kind of close together, so very short traces is in between, and you put your ESD protection device somehow close to the PHY, because you do not have long traces allowed. So then especially then, you really need to, when choosing external ESD protection, you need to look on the on-chip ESD. Yeah, you can do the classical way and take 10 different ESD protection devices, put it on your PCB, and see which works best. Yeah, and choose the best. This is you still can do. Yeah, but you can do the investigation much more systematically and much deeper analysis by investigating this on-chip ESD, which you see on the right side. You can create using Yeah,
I think we should mention why this is important, because the on-site ESD protection may be, for example, for a lower voltage, and then if we place the external component for a higher voltage, then it's going to be useless, basically. I think it's on one of the next slides. Yeah, exactly. On the next slide it is.
It is on one of the next slides. What you want to do is the target is, and when the pulse is approaching here. So you want to flow, so the pulse go over the external ESD protection, because this is what it built for. Yeah, the external is built for clamping the pulse down to ground, and you want to avoid that the pulse is going to the on-chip ESD. Yeah, because it's only robust up to a certain level, usually 2 kV or somewhere in this area. So, and you want to protect the phi. Yeah, and yeah, the voltage ranges are very important. And then you can do, measure the IV curve of your on-chip, and then for sure also measure the IV curve of your external ESD protection. And then you need to match. Yeah. And as we said, this is not very good. So whenever you have the case that when the external ESD protection device is triggering at higher voltages, and not only triggering, much more important, clamping, clamping at higher voltages compared to the on-chip ESD. So red curve related to on-chip, blue or petrol related to off-chip. This is not a good, here this will not work in your system, So here in this scenario, the on-chip will go in breakdown earlier, and clamping and most probably will be damaged, and then your phi is damaged, this is what you want to have, ideal case, meaning your voltage range so the trigger voltage, but at least the clamping voltage should be of the on-chip should be of the off-chip, sorry, of the off-chip ESD protection should be below the on-chip ESD. Then you're safe. Because then when pulse is approaching, the external will trigger, and after a very short period of time, a few nanoseconds, it will clamp. And once clamping, this is the path for the current, low impedance path for the current, and then you're safe.
Yeah, definitely.
This is very important. And so we did here a lot of investigations with some partners in automotive, but also in mobile consumer applications. We have some experience here. We also can do some simulations, some seat simulations to prove this concept. We did it several times here, and very, very good.
Okay, so just make conclusion. If someone would like to, or someone needs to decide on what kind of ESD chip they would like to use, they can, for example, go on your website, and I guess you have there. Can we show your website? I'm curious.
Yeah, maybe. Oh, it's still not. Give me a second. Can you see this?
Yes, I can see it. So how would you select? How for example you would find USB ESD protection?
So this is products, and then you have some of them. ESD protection, filtering. Then you have kind of clustering. So this is automotive. So this is ESD, general ESD protections, EMI solutions with integrated protections. This is kind of common mode filters, small common mode filters combined with ESD protection devices. Very cool. And then we have transient voltage suppressors. And so based on wording or definition, those are kind of bulky devices which you put on VBus, for example. So for surge protection.
Or power of you can use it for Okay, but let's search for USB ESD protection. I'm curious how easily you can find it.
Yes, so for automotive here you can automotive ESD, so general one, automotive Ethernet, LIN, CAN, infotainment, and SADIS. So you might go here, and then you will get some selection. So there are some Ethernet, but here you have USB.
Okay, it's directly in the name actually.
Yes,
that's cool.
And so different packages, bidirectional, unidirectional. So there are sometimes. So usually we recommend bidirectional, but some specific requirements might need a unidirectional. So here, device capacitance.
So how do you choose from all these?
Yeah, based, as I said, when you have used before, for example, so you need to go to very low device capacitance, yeah? So this one, 0.2 or 0.24, yeah? Or we have in mobile, so this is for automotive. For mobile applications, we even have 0.08, so 85 femtofarads, a very, very low device capacitance, yeah? And you can choose like this, yeah?
Perfect. Thank you so
Okay.
much, Andreas. This was super useful. I really hope other people or everyone who is watching this video also will find it useful, and maybe I really hope they learned something new.
Yes, yeah, I hope. Thanks, Robert, for inviting and for having this very nice talk. It was very fun, and I hope, yeah, some useful topics and content for your viewers.
Okay, thank you.
Thanks.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.